So if you've been paying close attention in the first couple chapters, you might have a question at this point in the lectures. And that question might look something like this. If natural chlorine already existed in the stratosphere because of natural emissions of methyl chloride from the oceans, why did we only start seeing the ozone hole appear in the late 1970s? I mean, we had the polar vortex around the South Pole before that during the winter months, and the conditions for the activation of inactive chlorine during those, on those polar stratospheric clouds in the winter months, followed by ozone destruction in the early and late spring, should have still been occurring. So why is it only in the late 1970s that we started to observe ozone destruction on a massive scale and the opening up of this ozone hole? The answer to this question is more easily explained if we look at a little bit of history, particularly in the United States. So post-World War II, the United States saw an industrial boom, and that led to a dramatic increase in anthropomorphic emissions, or simply man-made emissions of all kinds of gases and particulate matter. Especially in the early 50s and 60s, there wasn't a lot of regulation over emissions. And with the dramatic increase in industrialization, we started to see emissions on megaton scale. And one of the classes of molecules that started to be emitted on significant scale during this time period is a class known as CFCs, or chlorofluorocarbons. These compounds were used in refrigeration and air conditioning. Actually, they were invented around 1930, had amazing properties that made them perfect for refrigeration and air conditioning, both processes of which essentially function in the same way. And it's really these compounds that allowed for the widespread distribution of refrigeration units and air conditioning up through the 1970s. And we can actually see, if we look at the emissions of a couple of different chlorofluorocarbons, so many of these are given numbers, a couple are illustrated here. So CFC11, that's trichlorofluoromethane. CFC12 would be dichloro-difluoromethane. And we can see here, this is in essentially kilotons of emissions or production in the US and the rest of the world. And here we've got the, I think we've got the US and the rest of the world, and then we have kind of the aggregate data of the two combined. And what we'll see is that early in the 1930s, during the Depression years, there's not really any emissions, but then, and up through World War II, but then after that, we start to see this dramatic increase. And the dramatic increase in CFC production and thus emissions, because many of these refrigeration systems were not well sealed, there was really no control over what happened to them after they were disposed of, and so much of these gases simply were emitted into the atmosphere. And there was a really nice correlation between this increase in CFC production and the onset of the ozone hole. So that leads to another question. If CFCs are being produced and emitted into the atmosphere, then why aren't CFCs simply removed or destroyed in the troposphere like many other gases are? The reason for that comes from a little bit of reaction energetics or enthalpy data. If we think about the main species in the atmosphere that's responsible for oxidation of gases, primarily we think about the hydroxyl radical here. But if I try to react a hydroxyl radical with, in this case, CFC12, so dichloro-difluoromethane, if you try to abstract a fluorine off of this, what we notice is that this is essentially a very endothermic process. It essentially does not occur. It's uphill by 222 kilojoules per mole. We could think about perhaps abstracting off a chlorine rather than a fluorine, but what we'll notice is that's also uphill by almost 100 kilojoules per mole. There are other gases in the atmosphere that are responsible for various oxidation reactions, one of which is nitric oxide. And we could think about that abstracting off a fluorine or abstracting off a chlorine, but we'll notice in both cases just looking at the enthalpy for reaction, these are all very endothermic processes, very uphill, and essentially the rates are so slow, we essentially don't consider these as happening at all. Another way of looking at this same information here is to look at the bond strengths. So what I see on the reactant side is I'm looking at a carbon-fluorine bond or a carbon-chlorine bond. And then on the product side, I've made a new oxygen-fluorine or oxygen-chlorine or nitrogen-fluorine or nitrogen-chlorine bond. And if I simply compare some of those bond strengths, then the fact that this reaction or that these reactions do not work makes some sense put in this context. So on the reactant side, I'll notice the bond strengths for a CF bond or a CCl bond are fairly strong, 485, 327. These are fairly strong bonds, particularly the CF bond. If I compare that to the OF bond or the OCl bond, these are now significantly weaker, sometimes even less than half the strength of the CF bond. So if the bond strength on the reactant side is stronger than the bond strength on the product side, the reaction's not going to be favorable to go in that direction. And we see the same thing occurring if we compare the NF or NCl bonds to the CF and CCl bonds. Those are significantly weaker, perhaps not the NCl bond versus the CCl bond in that particular case, but still it's an uphill reaction in both cases. So that's why CFCs aren't removed. There's no tropospheric sink for these reactions or for these compounds to decompose them in any way and bring them out of the atmosphere. So what happens is they rise up into the stratosphere. And then the next question is, well, what happens to them after they enter the stratosphere? Well, it can take quite a while, but they will eventually rise up to the mid or upper stratosphere where the UVC light intensity starts to be a little bit greater. And what we'll see here is then they absorb generally in the region of 220 to 290 nanometers. So that's in the UVC region primarily. And that will result in the cleavage of a CCl bond. So that's the weaker of the two bonds there, the CF versus Cl. It will result exclusively in the cleavage of the CCl bond, but that liberates now a free chlorine atom into the stratosphere. That free chlorine atom then goes on to react with ozone to undergo all of our normal ozone destroying sequence of reactions. And so the net product here is that the increase in production and emissions of CFCs, coupled with the fact that there's no tropospheric sink for the CFCs, results in a dramatic increase in CFC concentration in the stratosphere, which then directly results in a dramatic increase in the free chlorine concentration in the atmosphere. And thus we start to see ozone destruction on a significantly larger scale now than we would have seen simply with the natural level of emissions from methyl chloride.